So, welcome everyone to the session 8 of this course, Microwave Engineering. So, today's session will be having discussions on microwave amplifiers and oscillators. Uh, the topic of discussion of the video lectures uh, are two-port power gain and stability. So, basically the design of a single stage transistor amplifier, then a low noise amplifier design, then discussions on RF oscillator. So this is the content or the syllabus coverage in this particular week 8. So I have I would like to have a short discussion of some of the basics about microwave amplifiers and oscillators so that we will be able to go through a few MCQs, basically the conceptual based questions, and also a very few numericals. So let's start with looking at the representation of a two-port, as I said before, two-port network, which is an amplifier. As you see here in this, so this is being represented by so any transistor on an amplifier is represented by its on scattering matrix S, and the feed line's characteristic impedance is Z0. Okay, and if you notice, this is the source voltage Vs, and this is the source impedance Zs. And if you look at this, this is the port 1. So this is the port 1 and this is the port 2. And at the port 2 or at the output port, you have the load connected, that is ZL. And if you notice, so the incoming voltage to port 1 is V1 plus and the outgoing voltage at port 1 is V1 minus. Similarly in port 2 also. And the important thing here to understand is about this gamma S and gamma L. So that is your reflection coefficient. So this is source reflection coefficient and this is load reflection coefficient. And if you notice, this is gamma in and gamma out. So these are the input reflection coefficients. So if you see this arrow mark, it is looking into the two port, into the port 1 or into the transistor amplifier's input side, and this is towards the output side. So it's clear that one is the input reflection coefficient and the other is the output reflection coefficient. So we will have lot of discussions about these reflection coefficients. Okay, so let's move on to a simple question. So tell me, if you could say, what are the important considerations in an amplifier design? So you can even type in the chat or unmute yourself and answer this question. Tell me what you think. What is needed to be considered when you design an amplifier, or what are the criteria, or what are the important parameters? At least we can talk about the parameters.
Ma'am, reflection coefficient.
Okay, fine. So in a way, it is going to be affected by the reflection coefficient. That is fine. But in general, what is the purpose of an amplifier? It's giving you some gain, isn't it? So
Yes,
one
ma'am.
of the considerations is about the gain of the amplifier, and another is the stability of the amplifier, on which stability which is eventually dependent on other things, as you said, the reflection coefficient and all that. Okay, and then comes the noise figure. This is a very important parameter, and you all know about this noise figure. Okay, so these are the very important considerations in any kind of an amplifier design. So now, in case of a microwave amplifier, we'll narrow down our discussions onto this microwave amplifiers. So let's move on to looking at the different gains in the beginning. So as you see here, in the second circuit over here, you can notice that this is the transistor S matrix, and as you see here, you have an input matching network, and at the output, you have an output matching network. And if you notice, this is the source voltage. So basically, this matching network is going to match match the impedance of this side to this source side. Similarly, from the output transistor side to the load side. Okay. So that is the purpose of these matching networks at output and input. Now let's talk about this power gain. So what do you mean by power gain? So these are some of the concepts discussed in the video lectures. So let's just take the brief of that. Okay. So the ratio of power delivered to the load to the input power is called the power gain. So this is a very simple definition of a power gain. Ratio of power delivered to the load to the power input or input power. Okay. Then you have come across something called as available power gain. Okay. So that is your available gain. Okay. You can say that available gain. So the available gain is nothing but the power available from the network by the power available from the source. So this is the ratio of PAVN to PAVS. So that is your available gain. And the third terminology which you have come across is a transducer gain. Okay, transducer gain. So this is the ratio of power delivered to the load, okay, to the power available from the source. Okay. So now, if you notice the transducer power gain, this GT, okay, this is going to depend on ZS and ZL? I have this question to you. So this is a question. I'll repeat the question once again. The GT, the transducer gain, is it going to depend on ZS and ZL? So if you notice, what is transducer gain? It is ultimately what power is being delivered to the load. So obviously, it has a dependence on ZL, and also it is a ratio to power available from the source. So power available from the source is again going to depend on the ZS. Okay, so I think I have already given away the answer, so there is no point in asking. Yes, that is a right thing. So this is going to depend on, the GT is going to depend on ZS and ZL. That is the source impedance and the load impedance. Okay, now the available gain. So we have talked about this available gain. Okay. So this is the ratio of available power from the network to available power from the source. So this is relevant only when it's a perfect matching condition. I mean, at the input side, there is a perfect matching. At the output side, there is a perfect matching. Then we can take this ratio to be relevant. I mean, the gain to be relevant. Okay. But unless it is perfectly matched, it doesn't give you the actual gain of the transistor amplifier. And I just wanted to brush up on this. If you remember, there is something called as unilateral transducer. Can you tell what is S12 in case of a unilateral transducer, S12?
0, madam.
Yes. Okay. So just, and other thing to touch upon before we go in, I think we will go through some of the MCQs. Okay. I think before that I have a few more questions. Okay, let's see that also. So tell me, if gamma S and gamma L are 0, then what is GT? So gamma S is the reflection coefficient, so source reflection coefficient, and gamma L is the load reflection coefficient. So then in that condition, what is the uh, transducer gain? Transducer gain, if you remember, transducer gain is the ratio of power delivered to the load to the power available from the source. Yes, please, yeah, yes, as you all said, the GT will be GT max. Okay, yes, GT is GT max, but then what is the value of that? It is modulus of S21 square. Okay, so I hope you have come across this in the video lectures. Okay, so just trying to, okay. Then the other question, in case of a unilateral transducer where S12 equal to 0, uh, the equation for um, GT, that is, so GT is the transducer gain is, so GTU indicates the transducer gain for unilateral transducer. So in that case, GTU is, so please note down this equation, which is very useful. Hope you already know this. Mod S21 square is into 1 minus mod gamma S square into 1 minus mod gamma L square divided by 1 minus S11 into gamma S square 1 minus S22 into gamma L square. So this will be useful to solve the numericals. So just have a idea of what is GTU. That is, in case of a unilateral transducer, the transducer gain, the transducer gain. Okay, now coming to what is the condition, I mean, unconditional stability of the amplifier can be ensured under what condition? In case of amplifier, unconditional stability condition.
Mod of gamma in is less than 1.
Yes, yes. Right. Mode gamma in less than 1. Mode gamma out less than 1. So these are the condition for the unconditional stability. And this is for all passive source and load impedances. Now I think we'll move to some some question. So we'll come back to oscillators. Before that, we'll go through a few questions on a few MCQs on what we understood about the amplifiers. So please go ahead with the first question. So the first question is, the overall gain of a transistor is always a fixed value and cannot be changed as per design requirements. Overall gain of a transistor is always a fixed value and cannot be changed as per design requirements. The question is about overall gain. I repeat, the question is about overall gain. Okay, so I think many of you have answered. So let me tell you. So the overall gain. So for a given transistor, say gain G naught. So gain is fixed. But if you see the overall transducer gain, that is going to depend on the gain of the matching network. Okay. So this matching network, if you remember, you have this input matching network and you have this output matching network. So that overall gain will be controlled by this gain of these network also, that is GS and GL, okay, which is possible to be changed. So the answer for this question is false. Overall gain, okay, so that parameter is very important, overall gain. So if you notice here, this is
Hello,
G
madam.
naught.
Madam, once again repeat the concept, madam. Why gain, overall gain is not changing?
Okay. So I
Ah,
told this is the transistor. So transistor gain is G naught. Okay. Now you have an input matching network and output matching network. So the overall gain is being controlled by all these three, GS, G naught and GL. So if that is being changed, okay, then you have the possibility of changing the gain. So the question is about overall gain. It's not about the transistor alone. So if it was about G naught alone, then you can say it is fixed. G naught is fixed. For a particular transistor, G naught is fixed. But now here it is with GS and GL. So it is not, it can be changed as per the design requirements. I hope this makes sense.
okay, madam.
So now going to the next question. Maximum power transfer from the input matching port to the transistor. So you can imagine from the input matching network to the transistor. When the maximum power will be transferred? Very simple question. I request everyone to answer this. Yes, you are right. Maximum power will be transferred when gamma in is equal to gamma S conjugate. Okay. So if you just look at this, maximum power transfer from the input section to the transistor will happen only when gamma N is equal to gamma S conjugate. Okay. Similarly, gamma out is equal to gamma L conjugate if you want to transfer maximum power to the load. Okay, that is the next question. I think I have already answered that. Yes. Okay. Question number 4. I request everyone to answer. Condition for maximum power transfer from the transistor to the output matching network. Answer for question number 4. Yes, that's the right answer. Gamma out is equal to gamma L conjugate. Okay. Now, okay. Let's move to the next question. Question number 5. The input and output ports of an amplifier are always matched to the impedance Z0. So if you remember the network which I have shown you before, you have a transistor and on either sides you have the matching networks. And So this is G naught, GS and GL. So this is the input matching network. This is the output matching network, and this was the transistor. And if you remember, it was represented by this S matrix and it was written as Z0. Why it was written as Z0? It states that the input and output ports, okay, it was written as Z0 here, okay. So that states or that indicates that the input port and the output port of this is being matched to Z, okay. So this is a true statement, as you all said. Coming to the next question, unconditionally stable devices can always be dash for maximum gain. Lossless matched, conjugate matched, forward biased, driven with high current. Unconditionally stable devices can always be, yes, right answer, can always be conjugate matched. Okay. Now coming to the next question. In terms of S parameters for a transistor, transducer gain. So in the beginning of today's session, I told about the transducer gain, which is the ratio of power delivered to the load to power available from the source. So in terms of S parameters, how do you write this transducer gain? Any idea how it can be written in terms of S parameters? Yes, Dr. Hemant Kumar, you are right. The answer is mod S12 by mod S21. So you know that transducer power gain is the ratio of measured power at port 2. So port 2 is basically what? The output port. Okay. Output port or port 2 to the power at the input port. Okay. Power at the input port or port 1. So it can be redefined. Say, you know what is S12 and S21. So when we say S12, basically it is the transmission from 2 to 1, and S21 is basically the transmission coefficient which indicates the transmission from 1 to 2. Okay. So it can be redefined in terms of what? S12 divided by S21. Sorry, with the modulus sign. Hope this is clear. How do we redefine this transducer gain in terms of S parameters of a transistor? If there are any doubts, please ask or we'll move on to the next question. Okay, now we have a small numerical. I request everyone to try this out. In the S matrix of a transistor, if the parameter S21 is 2.6, then gain G0 of the transistor has the value. So you are given with S21. Can you find G0? And if you notice, that is in dB. You have S21. So the important thing to understand here is what is S21. S21 indicates the transmission coefficient from port 1 to port 2. Some answer has come 8.3 dB. Can you please answer? How did you get this 8.3 dB? I think two of you have answered option B. Okay, yeah. 20 log of S21. Right. So it's being taken as 20 log of S21. Okay, fine. So let's move to the next question. It's about the stability. Now we have a few questions on stability of a transistor amplifier. Okay, for a transistor amplifier to be stable, either the input or output impedance must have a real negative part. Okay, you are answering that it is true. So any reasons? So if you imagine if the input or output impedance, if it is having a real negative part, what would be the gamma in? If there is a real negative part for the impedance value, what would be gamma in?
Ma'am, for conditional stable, gamma in less than 1.
So what is gamma in? How did you arrive at that gamma in is less than 1? I hope you understood my question. How do you evaluate this gamma in? Is it Zs minus Z0 by Zs plus Z0? So,
Z0 minus Zs on Z0.
so then gamma S, how about gamma S, the source reflection coefficient? So, if you remember, there are two parameters. There are two types of reflection coefficient. One is gamma S and the other is gamma in. So gamma S is basically the reflection coefficient when you look towards this matching network. And gamma in is when you look towards the transistor. So my question is, suppose if you have a real negative part for the source impedance. Okay. Then how do you say that gamma in value is less than 1 or greater than 1, whatever it is? So I have a chat answer something. Reflection coefficient is 1, maximum power transfer to the load. Okay, I have a comment here. When reflection coefficient is 1, then you have the maximum reflections. Okay, so where you are saying the reflections? Suppose if you have reflections at the load end, then maximum power cannot be transferred to the load. So reflection should be minimum so that we transfer maximum power. If you are talking about the load side. Similarly, at the source side, from the source, if you want to deliver maximum power to the transistor, then the reflection should be minimum. So another equation is Z in minus Z naught by Z in. I think it has Z in plus Z naught. Okay. So you have okay, if we take this equation, Z in minus Z naught by Z in plus Z naught, and if you have a negative real part Z in, okay, if you have a negative real Z in, then the modulus of that will it be greater than 1 or less than 1?
Greater than 1, ma'am. Modulus means positive value only.
Yes. So then in that case, so you have the modulus of gamma in, sorry, I am not writing. So the modulus of gamma in will be greater than 1. Similarly, if you do the same for the output reflection coefficient, the modulus of gamma out will be greater than 1. Okay. So I'll repeat this here. Gamma in is basically Z in minus Z naught by Z in plus Z naught. And we are saying that this will have a negative real part. So then if you take the modulus, it will be greater than 1 or I mean in the gamma in could be greater than 1. So in that case, so let us come back to our question once again. For a transistor amplifier to be stable, either input or output impedance must have a real negative part. Is it true or false?
False. False.
So what is the condition for stability in case of a transistor amplifier? Mod gamma in should be less than 1 or greater than 1?
Less than 1.
Yes. So this is false. Okay. So let's go to the next question. Stability condition of an amplifier is frequency independent and hence can be operated at any frequency.
False.
So let us first look at the two statements in this single statement. Stability condition of an amplifier is frequency independent. Yes or no? Is it frequency independent? Stability condition. So let me elaborate on this. So the stability condition is going to depend on what? The input and output matching network. Okay. And that is going to depend on the frequency. So the first statement itself, here it is frequency dependent. Okay. And so because it is frequency dependent, so basically an amplifier which is, say, it is designed for a certain frequency will be stable at that particular frequency and unstable at other frequencies. Okay. So, so this answer is, so if you want to answer this question, it's like stability condition of a amplifier is frequency independent and hence can be operated at any frequency. So basically I should have given us two statements in fact. So the first statement is a false statement. So because it is frequency dependent, it can be, so when if you operate at a different frequency, definitely it is going to be unstable. So I would not like to take this question as a true or false statement, because inside that there are two statements and it's a bit contradicting. So I hope you understood the concept. Stability condition is going to depend on what is gamma in and gamma out, which is basically frequency dependent. So it is, this first statement is false. And why it can be operated, whether it can be operated at any frequency, that is kind of a confusing statement, because say it is stable or unstable could have been the question basically. So at the designed frequency maybe it's stable, if at the other frequencies it could be unstable. Okay. Yeah. Okay, now we have a small numerical. I would like you all to try it out. So you are given with the S parameters of the transistor. Please do calculate the delta. So if you remember, delta is one. K value, K delta test is something which we all do for evaluating the transistor if it is unconditionally stable or not. If you remember, we evaluate or we estimate what is mode delta, which is basically the determinant of the matrix S11, S12, S21, S2. You know what is the determinant of this. So this is S11, S22 minus S12, S2. So if you evaluate this, you will get what is delta. Can you please quickly find this out and the final answer for delta? So remember these are, okay, let me just wait for answers. I request to do a calculation once again. I hope you have considered the complex numbers as such, and finally, you take a modulus of that.
Option A.
Okay. So now you have recalculated, I think. What was the mistake before? Maybe you can help others.
Approx 0.3144.
Okay. 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 So you are saying that it's not exactly 0.336. Okay. Okay. Fine. Fine. So let's wait for a few more minutes so that everybody could try again.
Madam,
Yes.
the answer is 0.3137 only it is coming, madam.
Okay. Okay. Fine. Fine.
Two times I put same answer only I am getting.
Okay. No problem. No problem. Just waiting for everyone to.
Oh, okay, madam.
Hope everybody got the same answer 0.3125. Okay, 0.3144. Okay, there is a slight change. Okay, fine. So I think yes. So let's move to the next question. By performing K delta test for a given transistor, the values of K and delta were found to be. So these are the values for K and delta. So this is K and this is delta. So transistor with these parameters has unconditional stability. Is it true or false? So for that, you should understand what is the condition for K and delta. What is the condition for K and delta? If it is to be unconditionally stable. Any answers from you? What should be K and delta? The K delta test for the transistor stability. Mode delta should be greater than 1 or less than 1. Answers. I hope you remember from the lectures. Mode delta should be less than 1 and K should be greater than 1 in case of a unconditional stability. So here, is it true or false? So here K is not greater than 1, but delta is less than 1. So this is false. This does not have a unconditional stability. So very important, this K delta test for unconditional stability. Please note this, that is K value should be greater than 1 and mode delta should be less than 1. Okay, now we will go to a few questions about transistor. Okay. Let's have a look at this question. Second question. Transistor has the following S parameters at the operating frequency. So you know S11, S12, S21, S22, all values are given to you. The reference impedance, that is the Z0, is given as 50 ohms and source resistance is 50 ohm and the load resistance is 75 ohm. What is the transducer gain? So in the beginning of lecture, I told about the transducer gain equation in terms of S parameters. S parameters and also gamma S and gamma L. So here, what is gamma S? Zs minus Z0 by Zs plus Z0. Any answers for gamma S here in this question? What should be gamma S?
0.
Yes, right answer. So similarly, what should be gamma L? I am asking for this question.
Point 2.
Yes, 1 by 5. Okay. So now this gamma S is 0. So this term is going to be 0. And you need to see that it's a transistor is a unilateral circuit. So S12 is 0. So from S12 equal to 0 information, it's clear that S12 is 0. It is clear that it's a unilateral transducer. That's why we have taken this equation for transducer gain. Now, this has to be substituted. The rest of the parameters has to be substituted. S21 is 3.2 So it's a modulus of S21. So you can take 3.2 square. Okay, I give some time. I request everybody to just make this calculation. Remember, gamma s goes to 0 and take wherever modulus is required. So I think a few answers have come here. Uh, so let me just I request I think just okay, just let me clarify the step here. So mod S21 square is 3.2 square into 1 minus mod gamma L square. So that is 0.2. So gamma L is basically 0.2 square, that is 0.04. So divided by, so you know that the first term does not exist. So the second term, if you notice, 1 minus S22 into gamma L. So you know that S22 is in polar form, 0.5 angle minus 45. So that has to be taken or converted to a rectangular form. So when you convert this to a rectangular form, it becomes 0.354 minus 0.354J. Okay. So that will be multiplied by 0.2. Okay. 0.354 minus 0.354J multiplied by 0.2. Okay. And this has to be taken a modulus. The whole terms modulus has to be taken and then take a square of that. So the final answer what I am getting is 10.94. But I see that there are multiple answers. So probably I request everyone to recheck. I will also recheck. So yeah, I think the concept is clear. Huh?
Madam,
Yes.
in denominator, S22 is modulus only, no, madam. We have to take only 0.5.
S22 into gamma L, right? So it's not modulus, no, in the inside the, so if you, so this is, the whole thing is the modulus, right?
Okay, madam.
So I think I can show the equation for just a minute. Yes, some question. Is there a question? Okay, fine. So let's move to the next question. The transistor used in an amplifier has mode
Excuse
S11. Yeah, please.
Can I ask one question? Actually, it is very silly question.
Okay.
What do you have to exactly mean by this transducer gain? How it is actually different than the real gain? Because normally on the base of equation and all, we are deriving that thing.
Huh.
But just I would personally like to know that why it is mean to be what has to be mean by this transducer gain? Why it is so?
Okay. So in the beginning of the session, I mentioned about the different gains. So if you notice, okay. So I spoke about power gain, available gain, and transducer gain. So if you look at the basic definitions of that, so let's think about this way. So power gain. So when we say power gain, generally we say like the output to input. So here in this case, it will be the power delivered to the load divided by the input power. So that's the general fact which we all know. That is the power gain. How much power is being delivered to the load to how much is the input power. Okay. Now,
Yes.
now this is going to so in this case a transistor amplifier. So this is the transistor unit and it has an input side and an output side. So input side where the source is being connected, output side where the load is being connected. So if you have to have a, then you should have a matching network, the corresponding matching network, such that we will have maximum power transfer here also and also from here to here. Okay, that's the purpose of the matching network. That is evident to you. Now, what is transducer gain? The transducer gain is nothing but power delivered to the load to power available from the source. So then that is going to depend on this matching network. Suppose if the matching network is such that if this whole power, I mean this is input power, imagine that this is input power. Suppose the power available from the source is different from input power, then it's not, so transducer gain means how much power available from the source is being converted to the or is being delivered to the load. I hope this makes sense.
Okay. Thank you very much, ma'am.
Okay, so now let's move to this question. Yes. Okay. Transistor used in an amplifier. So S11 and S22 modulus of that values are given as 0.4 and S12 is 0. And S21 is 3 angle 80. Can you calculate the maximum transducer gain? So the maximum transducer gain, when will GT becomes GT max? Only when gamma S is gamma 1 conjugate and gamma L is gamma S is S11 conjugate and gamma L is S22 conjugate. Okay. In this condition, the transducer gain becomes maximum. So if you take the equation for transducer gain, GT max is modulus of S21 square into 1 minus modulus of S11 square into 1 minus modulus of S22 square divided by 1 minus modulus of S11 square 1 minus modulus of S22 square the whole square. Okay. Now, so this is after substituting gamma S as S11 So if you notice here, I have substituted gamma S as S11 and gamma L as S22. So if you see this, so this is square. So denominator and the numerator gets cancelled. And finally, you have mod S21 square divided by 1 minus mod S11 square multiplied by 1 minus mod S22 square. Hope this is clear. I request everyone to quickly calculate. You know the value of mod S21, that is 3 square divided by 1 minus 0.4 square multiplied by 1 minus 0.4 square. Please do a quick calculation.
Mod is
Option B.
3, ma'am.
Answer is option. Are you saying the option answer?
One.
I request. Okay, let's wait for everyone. Yes, 12.755 is the right answer. I hope everybody should be getting that. Anybody else who got the answer, please type in the chat. Yes, so I think 2 of you have got the answer. So the answer is option B, 12.755 or 12.76. Okay, thank you. Thank you everyone for answering this. Okay, so let's move to the next question. Okay, now we have a few questions about oscillator. Okay, so before going to that, let me tell you quickly what is the condition for steady state oscillations. Say you have a say R in, X in, so this is, and then you have a load ZL, which is RL plus JXL. Okay, and this is gamma in, and this is gamma L. For steady state oscillations, what should be the condition? For steady state oscillation, so the gamma in into gamma S should be 1. Similarly, gamma out into gamma L should also be 1. So this is the condition for steady state oscillation. So please keep this in mind. What is the condition for steady state oscillations? So far we were talking about the amplifiers. Now the discussion is on oscillators. So the very basic thing is what is the condition for steady state oscillation. Okay, then I wanted to discuss about the Colpitts and Hartley oscillators, which will come in the questions as such. So while discussing the question, we'll discuss that also. So coming to the question here. Okay. Okay. So you have a BJT with an input conductance GI. So you have GI value given to you, input conductance GI, and a trans conductance GM. So these are parameters with respect to the BJT, and you are going to design a Colpitts oscillator. So Colpitts oscillator has a capacitor connected to the base. Okay, there is a capacitor connected to the base with a value 0.75 nanofarad. Okay, please correct this, read it as 0.75 nanofarad. And the inductor used is 0.1 microhenry. So the question is about the resonant frequency F0, okay, in megahertz. So first let us see how a Colpitts oscillator look like. All of you know how it is. So let me just quickly draw. If you have a transistor based circuit here, just wanted to give a rough picture of the Colpitts oscillator. You have one inductor and which is parallel with the two capacitors in series. Okay. No, they are not in series. Okay, let me just. Okay, so you have C1 and C2 here. So this C2, which is connected to the base of the transistor, is being told as, what is C2? It is given in the question as 0.75 nanofarad. Okay. And the L1 is mentioned as 0.1 microhenry. Now, how do we find? So if you know C2, can you find C1? That's the first thing. So once if you know L1, C1, C2, it's easy to find the resonant frequency. So the only parameter which is unknown is C1. So is there a way to find C1? So for the so let us look at the condition for oscillation in case of Colpitts oscillator. C2 by C1 is equal to Gm by Gi. So Gm is the transconductance, Gi is the input conductance. So this is the condition for Colpitts oscillators oscillation condition. So from that, C1 can be evaluated. C1 is C2 into Gi divided by Gn. C2 is 0.75 nanofarad multiplied by 1 millisiemens divided by 25 millisiemens. Answers for C1? Any answers for C1?
Thirty picofarad.
Okay, 30 picofarad. Or 0.03 nanofarad. Now, what is the equation for omega naught? That is the resonant frequency. Okay, remember it's not omega naught which is being asked. It is F naught which is being asked. So you have to convert it back to F naught. So let me write the equation for omega naught. 1 by L3 multiplied by C1 plus C2 divided by C1 C2. So this is the equivalent capacitance and this is the inductor there. Any answers for omega naught or F naught? C1 and C2 are non. Just substitute in this equation for omega naught and you can find.
What about L3 value, madam?
Answers for omega naught or F naught?
Ma'am, in formula, there is L3.
Yeah, oh, it's not L3. I mean, it's just L1. I mean, so it's same. Inductor is only just one. I think there might be some mistake here. So please verify. The final answer is 93.7 megahertz. You should be able to get this, I think. Mostly you should be getting. I request you guys to try. So let me ask you this. If you have any other doubts with respect to the sessions, today's session or any of the assignment questions, please let me know.
91.7.
Oh, you are getting?
Yes, sir.
Okay, fine.
Omega naught is 5.76 into 10 to the power 8.
Okay. That's fine. That's fine. So make sure that you substitute in the correct. If it's nanofarad for C1, make sure that C2 both of them are in nanofarad, and ensure the right calculation for say the omega naught. Take into account of that units. So hopefully you will be able to get this close to 90 megahertz. Any doubts? So there is one question I would request you to try. Hartley oscillator. So because we have already done a question on Colpitts, you can try this out. A Hartley oscillator has the L1 and L2 values. Say instead of having C1, C2, L, a Hartley oscillator will have L1, L2, C. Okay, so you are given with all these L1, L2, C values. Can you find the resonant frequency F naught? So basically, you know, omega naught is 1 by root of C1 into L1 plus L2. 1 by root of C1 into L1 plus L2. So F naught should be 1 by 2 pi. The omega naught by 2 pi. Substitute L1, L2 as 12 millihenry and 4 millihenry, and capacitor value as 4 nanofarad.
Option A.
So what value you are getting exactly, the value?
19.9
19.9
kilohertz.
kilohertz. Okay. I hope, yes, that's the right answer. I hope others would also be able to get that. So there is a quick question about Colpitt's oscillator. So you are given with the operating frequency, I mean basically the resonant frequency, 50 megahertz. So basically this Colpitt's oscillator will have an inductor in the feedback session, then two capacitors. So as we discussed in the previous problem. So there are two capacitors and one inductor. So the question is, you are given with resonant frequency and also one inductor value. What should be those two capacitors? So if you know what should be the equivalent capacitance, then from the equivalent capacitance you should be able to say what should be the individual capacitors. Can you give it a try? So the idea is very simple. From the I'll just write quickly. You know that omega or resonance is 1 by root LC. Okay. So this C is nothing but effective C of C1 and C2. You know the value of omega or F. Okay. So let me write it as 2 pi F. So I can write it as 1 by 2 pi. So F is 1 by 2 pi root L C effective. C is known to you, F is known to you. Can you find C effective and then say among this option which would be the best to, which is the best to choose? Best C1 and C2. To get the C effective. And you also know that C effective is C1, C2 by C1 plus C2.
Option D.
Option D, 80 and 60.
No, ma'am, no.
Uh-huh. Or you said B, 150? Effective capacitance, how much you are getting?
I think there is a mistake.
You feel there is a mistake in the problem, numbers?
My capacity is testing 101.42 picofarad.
Okay. Okay, just say that again. See, effective capacitance is
101.42.
okay, 101 picofarad. Huh?
Yes, ma'am.
Okay. Okay, anybody else with the answers?
Madam,
Huh.
effective capacitance 1.0146 microfarad.
1.01 microfarad. Huh?
Yes, ma'am.
Mm. I think somewhere in the powers you have a mistake. Um,
Madam, 1.014 into 10 power minus 10.
okay, 1.01 into 10 power
Minus 10. ma'am.
minus 10.
Wrong.
Okay, so that is 101 picofarad, right? That should be the answer.
Yes, ma'am.
Okay, so the effective capacitance is 100. Say, take it as 100 picofarad for easy. Sorry. Okay. So to get that, what should be the choice of C1 and C2? I think there is a mistake in the options. Just not look at the options. So to get 100 picofarad as effective capacitance, you can choose say 200 picofarads. Then, so 200 picofarad, comma 200 picofarad. Then you can get the effective as 100. Please don't look at the options. I think the options are wrong. So as I told, as you all get 100, approximately 100 picofarad is the effective. So C1, C2 could be 200 picofarad so as to get this effective as 100. I hope this is clear. Any doubts? So if there are no doubts, we'll wind up the session for today.